Okay, well, let's continue now and talk about the energy levels in two-dimensional nanostructures. Hang on. Very good. So we're imagining electrons moving through a solid that encounter, excuse me, oh my gosh, a potential that looks like this, where the potential varies as a function of position. How do we treat something like this? Well, to begin with, we're going to use what's called the effective mass approximation. And that's exactly what it sounds like, but it's worth taking a second just to realize exactly what we mean here. What we're really saying when we use effective mass is we're saying that the wave function of our particle, of our electron, can be written as two parts. One part called the envelope, which varies slowly with position, times the second part, which is the block part of the wave function. Excuse me. Which is periodic. That is, it repeats in every unit cell of the crystal. Okay? And the idea then is that our wave function really looks something like this. So it has these two parts. On the one hand, it varies rapidly, oscillating at least once per unit cell of the crystal due to the block part of the wave function. But the overall amplitude varies slowly, like the envelope. Okay? And it's the behavior of the envelope part of the wave function that we want to be able to describe. And it can be shown, that's the professor's cop-out there. It can be shown, but I'm not going to bother doing it, that the envelope equation solves a type of Schrodinger's equation, which looks like this. H bar squared over 2m star, where m star is the effective mass, times the second spatial derivative of psi with respect to r, plus the potential energy, which is a function of position, times psi, equals E times psi. We're here, the wave function that enters into this equation is the envelope, not the entire wave function. And as a result, or along with that, the mass that enters in is the effective mass. Okay? And finally, the energy here is the energy relative to the band edge. For example, for electrons, it would be the energy relative to the minimum energy of the conduction band. Okay? So that's what our Schrodinger's equation is going to look like in the effective mass approximation. And then within this approximation now, we can figure out what the energy levels of two-dimensional nanostructures or quantum wells should look like. So now we're ready to talk about energy levels in quantum wells. So first of all, in quantum wells, the potential energy only depends on one variable, one direction, z, okay? But it doesn't depend on the other two directions because our layer is a thin film confined in one direction but extended in the other two directions. So we'll say it's confined in the z direction but free to move in the x and y directions, okay? In that case, we're going to use separation of variables to treat this type of problem. That is, we'll say that the wave function, little psi of r, so already this is the envelope part of the wave function, that we can write it as the product of two things. The first is, I'm sorry, we can write it as the product of several different functions. One part, z of z, is an amplitude that only depends on the displacement in z, okay? And describes how the wave function changes with, well, of course, with displacement in z. Times a second function which only depends on x, and a third function which only depends on y, okay? Then we can substitute this separable solution into Schrodinger's equation. And when we do this, we get the following, okay? Minus h bar squared over 2m times del squared times z of z times x of x times y of y, okay? Oops, excuse me. Plus v of z times the z function times the x function times the y function, and that has to equal to the energy times z x y. We did something similar in modern physics when we separated problems in 3 dimensions, and we're going to follow the same routine here. The next step will be to divide both sides by the product of the x function, the y function, and the z function. Well, actually, let me do one more step before that, just to make it explicit what we're doing. So this can be written as following. So first of all, remember that del squared, second spatial derivative, is just a shorthand for the following. Second derivative with respect to x squared, plus second derivative with respect to y squared, plus second derivative with respect to z squared, okay? And so our equation can be written as follows, h bar squared over 2m. And then notice, if we take the second derivative with respect to x squared of zxy, well, z function and the y function don't depend on x. So they're treated like constants to the partial derivative. And so we have z times y times second derivative with respect to x of the x function. Plus we have z times the y function times second derivative with respect to, excuse me for making a mistake here. Z times the x function, the z function times the x function times second derivative with respect to y of the y function, plus x times y times second derivative with respect to the z coordinate of the z function. Oh, that seems like quite a lot. Plus the z times z x y, and that's all equal to e times z x y. Okay, now we'll divide both sides by the wave function, by the product of the x function, y function, and z function. And then what we get is the following. On the left-hand side, we have minus h bar squared over 2m times, well, times this, plus the rest of the terms. And I wrote this out because I wanted just so you could see that in this product, in this fraction, several things cancel out. The z function cancels out, the y function cancels out. And we're just left with second derivative with respect to x of the x function divided by the x function. So applying the same logic to all the terms, we get minus h bar squared over 2m times second derivative with respect to x of the x function divided by x plus second derivative with respect to y of the y function divided by y plus second derivative with respect to z of the z function divided by z. Oh, right? Plus the potential is equal to the energy. Okay? And now we're going to do one more thing. We're going to divide this into pieces. Each piece only depends on one variable. Okay? Okay? Very good. So we have, just want to be careful enough to make sense what we're doing here. So first we'll have all the terms that contain the x function. Let me write it like that, so it's a little bit neater. That's one. The second term are terms that only vary with y. The third term looks like that. It contains all the terms that depend on z. And then all of these together add up to the energy, which is a constant independent of x, y, and z. Oh, and I should be careful. The mass here is the effective mass. There we go. Okay. Now, perhaps you remember how this works now. We have three terms, each of which only depends on one variable. The first term depends only on x. The second term depends only on y. And the third term depends only on z. And yet they have to add up to equal a constant. And this turns out to mean something very special. Not only does the first term only depend on x, but actually it can't even depend on x. It has to be a constant. And likewise, the second term is a constant. And so is the third term. And the reason is easy to see. Suppose that the first term that its value did depend on x. Well, since the first, second, and third term have to add up to equal a constant, and since the second and third terms don't depend on x, well, the first term then wouldn't be able to depend on x either. Because if we went from one point one value of x, one position in space where it was true, and shift it over to some other position in space, since this still has to be true, and since the second two terms didn't change, since we only did change the x coordinate, that would mean that the first term can't change either. So all three have to be constant. And since they're all constant, we may as well write them this way. We have the first term, minus h bar squared over 2m star. We'll call the constant that this term is equal to Ex, all right? And then we have a second equation. And then we have a third equation. Subject to the condition that the total energy must be the sum of Ex plus Ey plus Ez. Okay? Perfect. Now, we can rewrite these once more, and then the interpretation will be clear, okay? So perhaps you've been following along because you've seen this trick before, or perhaps you don't really remember it and you've been struggling to see what it all means. But in any event, now we're going to see what this all means. So I want to rewrite these expressions once more. So thanks for your patience. We'll just go through it once more. So now on the first equation, we're going to multiply both sides by the x function. And when we do that, we'll get minus h bar squared over 2m times second derivative with respect to x of the x function is equal to the energy, Ex, times the x function again. And we have an equation that looks exactly the same. For the y function. And finally, we have something that looks a little bit more interesting for the z function. Whew, there we are. Oh, I'm sorry, I left something out. How terrible. I left out the potential energy term for that equation. Okay, because we have a potential that depends on z. All right. Whew. Now, let's interpret these. Let's look at the first two equations. Now, do you notice what these look like? These look exactly like Schrodinger's equation for a free particle that can move in the x direction and for a free particle that can move in the y direction. So they look exactly like Schrodinger's equation where we've set the potential equal to 0. So that's what these describe. They describe a particle that's free to move, like a free particle, in the x direction or in the y direction. All right? So electrons in a two-dimensional quantum well are free to move in the plane. They're like free particles. But the third direction is different. In the third direction, the particles have a field of potential that depends on position. And so they aren't necessarily free to move in the third dimension, they're confined. Okay? Okay. And so what this is telling me is that the behavior of electrons in the plane and perpendicular to the plane are quite different. So and the wave functions that solve this equation look like e to the I kx or e to the I ky y. They're free particle wave functions. Or we can put these together and say that the total wave function goes like e to the I k parallel dot r parallel, where k parallel is a wave vector that points in the plane in some direction, and r parallel is a displacement in the plane. Okay? But the important thing is that they're free particles, so that their energy then is just given by h bar squared k parallel squared over 2m star. Where this energy here is their kinetic energy in the plane. We'll call it E parallel. On the other hand, the electrons are confined in the perpendicular direction. And there, the wave functions and the energies are described by Schrodinger's equation. For now, the thing that's playing the role of the wave function is just the part of the wave function that varies with z, what we call z of z. And the energy here is the perpendicular part of the wave function, which now I'll just call E perpendicular, okay? It's the part of the energy that's associated with the momentum in the perpendicular direction, momentum and potential in the perpendicular direction. Whew. Okay, here let's put a box around these two equations. These describing the free electron motion in plane, and this describing motion perpendicular, or the part of the momentum and energy associated with perpendicular direction. All right, here let's stop for a moment.